Continuing on with our population org here. A couple more technical terms today. We're going to look at a few graphs of populations. Um, we just talked about this discrete breeding that organisms go through. They reproduce once in their life, and then that's followed by their death. Versus continuous breeding. Nearly all animals fall in this continuous breeding strategy. I should say vertebrates. That would be the better answer there. All vertebrates go through that. Dandelions would be a boom and bust. They grow, they produce this flower, then they reproduce. They produce the white fluffy seeds that spread, and then they die out. Okay. A couple of terms here that we should go through is how populations grow. We'd already talked about that J-shaped curve. So exponential growth when it's growing at its biotic potential and there's no limiting factors, it is going to grow exponentially. All right. So it is going to keep growing at an increasing rate. And once again, this requires a limited amount of resources. A more realistic curve is an S-shaped curve or a logarithmic growth curve. And it has a lag phase, an exponential growth phase, a deceleration, and then a stable equilibrium. So we'll get a picture coming up here. And that's because it's reached its carrying capacity. Right. So if we're thinking about number of wolves that live in the boundary waters, as far as how much the boundary waters can hold, the boundary waters can probably hold more than 10 wolves, but probably less than 10 million, right? Like somewhere in between. There's a logical ceiling that no more population can grow in said area. Okay. So here's a look at that biotic potential. We see these numbers are increasingly, not only are they going up, but they're going up by more and more each generation. And that graph looks something like this. Okay, that exponential growth, here's that J shape that's going in there. And there's no factor to limit population growth. In reality, all right, in reality, what this looks like based on those last numbers is we get this exponential growth, but at some point it's going to reach this like, well, there's not really enough food or space or water or whatever that is going to be sustainable for us. So it's going to reach this stable equilibrium phase there. We won't worry about this too much. That's a little bit more too advanced math that we want. Sometimes the ceiling isn't met neatly. All right. Sometimes with carrying capacities, they don't kick in fast enough, and populations can actually grow well past the carrying capacity and then come plummeting back down. Here's a look at I can't remember the island's name, but there is a population of reindeer that got onto the island. And for a long time, there was no predators. There's plenty of resources. Life was good. And then they kept growing and growing and growing until they reached probably the carrying capacity was around 1,000, but they overshot it. There's a year where, hey, life is good. And they just kept reproducing and having offspring. And then all of a sudden, it wasn't good. All right. Famine strikes everything. And so it fell way off the back end because of lack of resources there. As a human population, we're currently in this front swing. We would like to have that nice, calm, stable equilibrium phase after this, where we just, population just kind of evens out, no growth, no death, that kind of thing. Living through something like this is horrific. That is not a fun time to be alive. All right. So I like pointing out Thanos here from the MCU. That was actually, I appreciate movie villains that actually have a decent premise, I guess, is the idea. His strategy is left a little bit to be desired because he just bought the universe some time. It wouldn't anyway. But he was also talking about that growing population, trying to apparently on his home world, this kind of growth happened. Population boomed, burned up all the resources, then it came crashing down. With those limiting factors, okay, there are things that limit how fast how populations can grow. Some are dependent on the density of that population. Others have no regard whatsoever. So I'll start with the first one, or the second one, I should say. Density independent factors. So these are things that happen that will happen regardless of how big a population is. Doesn't matter if you have 1,000 polar bears living in the area or 2 polar bears. If a natural disaster hits or it's a extremely hot summer for polar bears, that's going to lead to death. Okay, so whether other natural disasters are, doesn't matter what happened. Like if a hurricane's coming, it doesn't matter if your population is at a stable size or not. The hurricane's coming. The bottom one is much more dependent on how many organisms you have. Okay, the amount of food that's available, the amount of space, the water, parasitism, so like viruses and whatnot, competition. Those are all related to how large a population is. So as we go, like I said, here's a nice little picture from the book about a flood. All right, so it doesn't matter how big your population is; a flood's gonna claim some of it. That's for sure. Versus something like, let's get enough nesting spots here. Oops, nesting spots for our birds. If there's a smaller number of birds, then there's going to be plenty of nesting spots. And lastly, today, with populations, this is the best time I had to add this in there, is different species play different strategies when it comes to their population as a whole. Now, this is genetically related. They're not making these decisions actively. So cave strategists are like mammals. So we are these. They produce small numbers of offspring, and they usually invest a lot of time and energy into that offspring. Whereas our strategists are thinking about like insects, cockroaches, turtles. They lay tons of eggs. So they have large numbers of offspring with no care and low survivability. So the idea being, the first strategy, what humans do is, hey, we're only going to have a couple of offspring, but we're going to invest a ton of time and energy into them to make sure they survive. Where our strategists say, we're going to have the 10,000 offspring and we're not going to do anything with them after they're born. Chances are at least a couple of those will survive. So both are working out okay for the variety of species. Now, one's not better than the other. They're just two different strategies to play the evolutionary survival game there. So that's it for me today. Wrapping up here at the end of class. Make sure you stay on top of your work. You'll notice our last few assignments here are a little bit more I shouldn't say laid back. They're a little more simple. You can have multiple attempts at them. Just kind of the idea is making sure that we're finishing the class on a strong note. We will have a final next week. That is an ID final that you can, once again, take as many times as you want to, and I'll take the highest score. So good luck.